Our next speaker is Henning Seibel, and he'll be presenting the genesis and mineralization of offset dikes.
Good afternoon, everybody. I'm Henning. I'm the third PhD student in this overall Sudbury project, and my focus is the Sudbury offset dikes, which you can see here highlighted in the red colors, which are surrounding the main mass. And in today's talk, I would just want to give you a quick introduction on the different formation models for the offset dikes, as well as the overall mineralization style within the offset dikes. Okay, so as an introduction, we are talking about impact melt-bearing dikes today. And if we compare, or if we look at the impact sites we know on Earth, which are roughly 190, only a handful of these are report impact melt-bearing dikes, and only 2 of them report impact melt-bearing dikes which are wider than 10 meters and longer than a couple tenths of meters. And that's the Ferrífero dike here in South Africa, which is thought to be the largest impact dike on Earth, and the Sudbury impact and the Sudbury igneous complex, where we have the offset dikes, which is also one of the 3 largest impact craters on Earth. And only one is known which hosts syngenetic mineralization. That's, of course, the offset dikes here in Sudbury. So in this presentation, I just want to give you some information about the different models, as well as the different emplacement mechanisms, and talk a little bit about syn impact and post-impact processes, and on when does the mineralization form. So you have seen this geological map here already a couple of times. The offset dikes can be grouped into 3 types. They are the radial offset dikes. You can see them highlighted here in red, and they radiate away from the main mass of the Sudbury igneous complex into the country rocks. And they are often connected via funnels, such as here in Foy, as well as here in Whistle, or in Coppercliff and Worthington. But some are also not connected, or there's no connection visible, for example, here in Trill and Cascade. And these dikes represent injected impact melt from the melt sheet into the country rock at some stage during or after the impact. Then we have the concentric dikes, which are orientated subparallel to the SIC, which you can see in the north range for the Hess offset dike, and in the south range for the Manchester offset dike. And they don't have a visible connection to the main mass. And then lastly, we have discontinuous offset dikes, which are isolated pods of offset dike lithologies, which we'll talk about in a second. And they are hosted in breccia belts, and especially here in the South Range breccia belt, which is located where the Fruit and Stobie mines are located. And the name offset dikes comes from the primary discontinuities and the postmagmatic faulting, which offset segments of dikes. And you can see it, for example, here, where we have the Hess offset dike detached from each other due to a postmagmatic fault. There are 2 general offset dike lithologies, and the first one is the inclusion poor and sulfide poor quartz diorite, which is often abbreviated as QD. And you find the quartz diorite at the margins of the dike, which you can see here in the sketch from the Worthington offset dike in the gray colors. It can be chilled against the country rocks, and these chilled margins seem to indicate a very early melt from the impact melt sheet, which indicates that these dikes have been injected into the country rock very early. The second lithology is also a quartz dioritic lithology, but this time it's inclusion-rich and sulfide-rich. And you can see it here in the sketch in the red colors with the green clast, as well as here in the outcrop pictures. You can see it located on the bottom here and in the center here. And these IQD or MIQD lithologies, they often occur in the center of the dikes. And you can see this quite nicely here at the Trill outcrop, where we have the QD at the margins and then the IQD, which is mineralized in the center. And this is a typical setup where we have the QD at the margins and the IQD at the center, what we see quite often in the field. The overall mineralogy is quite simple for both of the phases. We have mainly plagioclase and amphiboles with variable amounts of quartz, minor biotite, granophyric intergrowth, and secondary mineralization. And overall, we have in the matrix, we have typically acicular plagioclase and is similar to spherolytic amphiboles, which is a characteristic point of the matrix of these dikes, which when you find this in the field, this is a good indication that you're looking at an offset dike, which these spherolytic amphiboles, which often occur at the margins, indicate a rapid crystallization of the melt. If we look at the inclusion-bearing quartz diorite, it has basically the same mineralogy, but in addition to the main silicates, we also find sulfides within the matrix. The overall matrix is more homogeneous and fine grained, and that is because we find lesser amounts of stellate and spherolytic amphiboles. But in addition to that, we do have a lot of inclusions, and this is something you can see here in this outcrop picture, where we have this homogeneous QD matrix. You can see the sulfide blebs in the matrix, and then we have here variable amounts of country rocks, inclusions. And these inclusions are often derived from the local country rocks, but they can be mafic and ultramafic with an unknown source, so-called exotic inclusions. And this is something Sandra has already talked about. These are often associated with mineralization, and we also often find QD inclusions, and this is something I will show you in a couple of slides and other images. If you look at the geochemistry of the dikes, we have already discussed that we find several units or lithologies which all have a quartz dioritic matrix. So if we compare this on a geochemical level within one dike, you can see that the trace element patterns are very similar. And as an example, you can see here the trace element patterns from the Worthington offset dike for the marginal quartz diorite, for heavily mineralized inclusion-bearing quartz diorite, for the QD inclusions within the inclusion-bearing quartz diorite, and so on. And they all have the same pattern. And this indicates that all of these lithologies are coming from the same melt source, or from the same melt. If we compare the dikes from a range, for example, the radial dikes in the North Range, and again, if we are looking at the inclusion poor QD phases as well as the inclusion rich IQD or MIQD phases, you can see that they all have similar trace element patterns again, which then indicates that all of these dikes have a similar parental melt source. If we compare North Range dikes and South Range dikes, you can see that there are some differences, and this could reflect differences in the country rocks, and this shows us that the initial impact melt sheet might not be entirely homogenized. And overall, the South Range dikes are more variable and more heterogeneous in their geochemical composition. If we have a look at the mineralization, Dustin has already touched on this. There are two offset dike mine, or there are two mines, active mines, which mine offset dike mineralization. For one, this is the Totten mine, which is located here in the Worthington dike, which is in production since 2014, and it's operated by Vale. And the second active mine is the Copper Cliff mine, or mine complex, which is one of the largest complexes here in Sudbury, also operated by Vale, and they are in production for over 100 years with some breaks in between. Besides that, the Fruit and Stobie mine complex, which is part of the South Range Breccia Belt, is the largest deposit in a mine complex in Sudbury. It has been mined out in 2016, and it's located here just north of the city of Sudbury. And besides that, we have a couple of smaller mines and smaller ore bodies, which are mainly located in the southern part of the Sudbury Igneous Complex, and a few are located here in the northern part. And there are also active exploration projects, such as the Norman West project, which is located here, where Glencore is exploring in the keel of this embayment structure within offset dike lithologies up to a depth of 3 kilometers. And another exploration project is located here at the beginning of the Worthington offset dike, and that's KGHM's New Victoria exploration project. On the bottom left here, you can see a long section from the Copper Cliff offset dikes. And you can see the north shaft and the south shaft, which is indicated in the map as well. And you can see the distribution of the ore bodies. And generally, the ore bodies have a subvertical plunge. And overall, the ores have 10 to 90% sulfides. So how does the sulfide mineralogy looks like? We have a typical assemblage of magmatic sulfides with pyrrhotite, chalcopyrite, and pentlandite. And usually we have a zonation which starts from disseminated sulfides to patchy disseminated sulfides to more semi-massive and massive sulfides. And here you can see drill core images with semi-massive sulfides, which have roughly like a metal content of 3% combined nickel and copper. And then, of course, we also have massive sulfides, which are here inclusion-bearing massive fractures with floating mafic and ultramafic class. And this image is from the fruit mine. So before I start talking about the different models and emplacement mechanisms, I just quickly want to recap some of the offset dike characteristics. So we've already seen that the inclusion pool QD is generally distributed at the margins and the IQD in the center. We can also see this in these field images here. And we've also seen this image before, and the IQD QD connects are often sharp, which you can see here, but they're also sometimes gradational. This is something you can see in this image here, where you can see that at some point the inclusions pick up, but it's not such a nice knife-sharp contact as we see in the left image. In addition, the QD and IQD matrices have a similar mineralogy and geochemistry as we've seen before, and we find frequent QD inclusions in IQD. And this is something you can see in this image here from the Whistle dike, as well as in the image here. And in a new publication from 2018, also IQD inclusions in IQD have been described, but this is something which is very, very rare. And I'll talk about that in a second. So based on the characteristics, some of the researchers and geologists here in Sudbury believe that the offset dikes form as multiple injections. And the way that works looks like this. We have an early sulfide-free and inclusion-free melt sheet, which then gets injected into the country rocks, forming this inclusion-poor quartz diorite. And then shortly after that, we have the formation of sulfides and of inclusions at the base. And these then get injected into the dikes again, into the center of the QD. And this would explain the often sharp contacts, which we can see, and the QD inclusions in IQD, which are quite abundant. And the reason that the IQD or MIQD is often found in the center is that the dike center from the QD was not solidified. And that means that there was a relatively small time gap between the two injections. And this is also supported by the matrices of the two lithologies, that they are both very similar to each other. Other authors believe that the characteristics of the offset dikes can also be explained by a single injection. And the model works like this, that we have an initial inclusion-rich and sulfide-rich basal layer, which then gets injected into the country rocks. And then during the flow of this MIQD unit, we have fluid dynamic processes which lead for the sulfides and for the class to rotate from the margins towards the center, and basically forming this inclusion pool margin, and then leaving behind in the center this inclusion-rich center. And this is something which could explain the gradational context which can be observed. And this is also something which might be able to explain IQD inclusions in IQD. But overall, the process of flow differentiation is not that well understood, and it has never been calculated for the volumes and for the sizes of dikes we are working with. This is a process which usually is applied to very narrow dikes. And it has also never been applied to dikes which are impact related. And there are a lot of uncertainties involved with this, and it's not clear if flow differentiation can actually be accounting the characteristics we see. And we believe that, at least for the moment, that the characteristics of the offset dikes rather support multiple injections. So next to the two formation models, there are also several emplacement mechanisms for offset dikes which have been proposed in the literature. And some authors link the dike formation or the injection of the dikes to the transit cavity formation. So the transit cavity formation is one of the crater formation stages, and it happens shortly after the impact, so in a timeline of seconds to minutes after the impact. So with the impact, we have the instantaneous formation of the melt sheet, and then shortly after that, some authors believe that we already form or inject this melt sheet into the country rocks. Other authors believe that the injection of the melts is linked to the rebound and central uplift and to the crater wall collapse, which are part of the early crater modification stage. So very large craters usually have a complex crater configuration, and this is something which also accounts for Sudbury, and this includes a central uplift as well as the collapse of the crater walls. And other authors link the dike formation to post-impact cratering stages, such as isostatic uplift, melt pressure increase, cooling, and readjustment. And these happen on a timescale of thousands to 100,000s of years after the impact. So overall, there are two general formation models and several processes which could explain the injection of the dikes. And of course, these processes have to explain the field characteristics we see. And here we have like a comparison matrix where you can see the processes here from early to late, and then you can see the characteristics on the right side. And I've already mentioned that the offset dikes seem to be an early impact melt. So this would, of course, can be explained by early processes. I've also talked about that we believe that multiple injections are more likely, but these multiple injections have to be in quick succession to each other. So we have to have two processes which happen in quick succession. And these have to be Bézin-White processes as well, which have to explain the QD and IQD relationships. And overall, all of these first features or characteristics can be explained by early processes, or we believe they can be explained by early processes. But one thing early processes cannot explain so far is that they not allow enough time for the sulfide exsolution and for the sulfides to settle down from the impact melt sheet. And this is something we are also currently working on, and this is something which Dustin and Sandra have already mentioned before, that we believe if the sulfur source does not come mainly from the main sheet, but there's a higher part of the sulfur source is from the local environment, and due to thermomechanical erosion, we might be able to explain a quicker sulfide saturation than previously thought. So in summary, the Sudbury offset dikes are the only known syngenetic mineralized impact melt-bearing dikes on Earth. Offset dikes usually comprise of an inclusion-poor, sulfide-poor margin and an inclusion and sulfide-rich center. In understanding their genesis might provide important constraints on the timing of sulfide generation and impact crater formation. And at the moment, our understanding is that that the formation mechanisms involve multiple injections as well as an early impact melt, which would indicate that we need a local sulfide formation. And with this, I would like to thank you, and I'm happy to answer any questions.
Thanks, Henning. That was great. There is actually one question already in the chat, if you want to take a look at that.
Yeah, open the chat. So the question is about the vertical ore bodies, which I've shown in the beginning, or subvertical ore bodies. And it is about, do you find consistent metal zoning for PGM and copper-nickel ratios, or are there different bodies, each unique forming slightly different timing evolving deposition conditions? I'll quickly go back to that slide. There is a zonation described in the ore bodies. And the zonation is that we usually have copper-rich ore further down than nickel-rich ore. So we might have infractionation of the ores, of the sulfides, where we have the copper further on the top, and then the nickel-rich ores further on the top, and then the copper-rich ore on the bottom. And we also see a zonation from close to the SiC to further away, and this could be this could be related to the erosional level, what we are looking at. So the overall impact structure was bowl-shaped. So at some point, we probably had an impact melt sheet which was lying on top of the sediment or of the country rock we are seeing now, which means that at the current erosional level, the dikes which are further away look at a deeper erosional level than the dikes, the dike sections which are closer to the SiC. And this is something which has been described in the literature, that the further away we are from the SiC, we do find more copper-rich ore. But overall, there is also a lot of heterogeneity within each ore body, and the ore bodies can be quite different to each other.
Perfect, thanks. So I think we're running a little bit behind, so I think we'll end the question period there. If anyone has any further questions, feel free to type them in the chat.